Let us start lecture 12. The course is corrosion protection methods, and the topic for today's lecture would be few more examples on better design to protect materials from corrosion. So, today will be the concluding lecture on the design aspects for corrosion protection. So, the course is better design. Now, we have talked about galvanic corrosion problem and better design in our last lecture. So, here we will be talking about examples on ion transfer. So, examples okay. Now, let us say we have a container, let us say glass container. This is a glass container. And here we have the electrolyte, say aqueous solution, and let us say it is a salt water solution. We have a copper coil, okay, copper heating coil, and here we have close to that heating coil we have a stirrer, and this stirrer, let us say it is made of aluminum and there is a rotation. Okay. So, this stirrer is made of aluminum. So, the glass container definitely it will not experience much of corrosion effect, almost nil corrosion. Now, the problem will be on the aluminum stirrer. Since copper heating coil is there could be copper ion formation. So, we can have copper ion, and this copper ion can transfer, can migrate from here to there, and it can deposit on the aluminum surface. Let us say here it can deposit by taking 2 electron and going to copper, and during that process aluminum can leave 3 electron and go to aluminum 3 plus. Of course, that electron balances will be maintained by, let us say, if we have 2 aluminum ion formation. So, that means 6 electron and there would be 3 copper deposition. So, here also 6 electron. So, then 3 atom of copper will deposit, and then you see that electron balance is maintained. Now, when we have a copper deposit here, so this is my copper deposit, and now we have a fantastic example of copper on top of aluminum. So, the locally this will be cathode, local cathode, and this will be anode, and this is local phenomena, and one can experience a small pit here. So, aluminum surface around copper deposit, it will form pit. Okay. So, that is a problem, fine, and that pit can grow, and since this is having a rotational movement, one point of time it can also break, because the pit is progressing inside the material. So, it can lead to a breaking of that particular stirrer. So, this is, we can say, bad design or poor design. The better could be, instead of aluminum stirrer, replace it with glass stirrer. Okay. So, this is replace aluminum with glass stirrer. So, this is a better design. Copper deposit effect and the pit formation will not be there. So, this is one example. Now, if we have another example like the ion transfer, on ion transfer, let us say we have a container which is steel made container. And same thing, you have a copper coil, copper heating coil. Now, the problem will be similar to the previous case where we had aluminum stirrer, copper ion will form and it will migrate or transfer, ion transfer can happen, and since copper ion has got a higher reduction ability than the iron, because copper is sitting on top of iron in that galvanic series in that particular solution. So, the copper deposit again would happen. So, this is the iron surface. So, copper deposit will happen. Same reaction, and iron will dissolve. And now, this copper deposit and the iron dissolution, that phenomena would happen locally. Again, it is a local phenomenon, and that would lead to another pit around this zone. So, here we will have pit on iron surface, and this pit will continuously grow, and then it might lead to a leakage in the steel container. So, there could be possibility, let us say here we have copper deposit and the leakage can happen around this zone. And interestingly, the leakage ability would be much higher around this zone than this part. So, less leakage, more leakage. In fact, less or negligible or no leakage in fact. Okay. The major reason here is we have copper coil close to the one of the walls of the steel container. Okay. So, if it is a rectangular tank, it is a circular tank, let us say. So, if we have a circular tank like this or a tank like this, let us say, if the tank is like this, if the copper coil is like close to this, so around this zone and the back of the surface, wherever this coil distance, the distance between the coil and the steel wall is very nearby, there the possibility of leakage would be more, because the ions need a little distance to travel from the copper end to the steel surface, and of course, it will deposit on top of steel surface and the local pitting can happen. But if we place this particular coil center of it, so the design modification would be, so this is my tank, instead of placing the copper coil close to one of the walls, it is better to place it at the center. So, the ion transfer, ion needs to travel a long distance and then the effect of leakage would be less. So, this is one possible design modification. So, putting the coil at the center. So, this is better. So, these are few examples on ion transfer. In fact, this ion transfer effect can be felt. So, if we increase the resistance of the electrolyte, for example, if we use salt water, if we use deionized water and if we use distilled water, we will see that the corrosion effect of the metal the metal container will be less in case of deionized water, because the resistance of the deionized water will be the maximum in 3 cases, and in fact the salt water would give the maximum corrosion of that container, metallic container, because that will have the highest conductivity. So, if we can prevent the ion transfer or put a resistance path to the ion transfer, we can definitely control corrosion to a great extent. Now, let us put some examples on stress raisers. Okay. So, examples on stress raisers. Or we can say stress concentration. So, this is again local effect. Any corner can give you triaxiality. So, let us say this is a sharp corner. So, it has a stress factor, local stress much higher than the surrounding area. So, this has two effects, one is stress, another one is, of course, there could be possibility of crevice, because a stagnancy is possible in that local sharp cornered area. So, this is one, and the second one would be crevice if stagnancy condition, under stagnancy condition. Fine. Now, it is better to give sufficient radius in those corners, so that stress concentrations can be, local stress concentration can be avoided. So, the better design would be, so this will be better design. So, it avoids both the things. So, this one as well as this one we can avoid. So, avoiding, if we do this, so both the effects avoidance. So, that means crevice is out, sharp corner is out, as well as stress factor is also out, local stress effect. This is one. Then there could be possibility of having some design like this. A kind of design like this. So, it is better to have, this is bad, one can have like this, like this, there is a sufficient corner again. In fact, if we have such kind of thing, it is better to cover it up. Okay. So, that time again this kind of coverage can avoid the crevice, as well as that corner can avoid. Avoidance of that corner can actually get rid of stress concentration effect. So, this is another one. Wherever there is a possibility of stress concentration, which is basically cornered region, we should make it a rounded shape. Okay. So, it is basically better rounded shape, as well as covering of the region wherever there is a possibility of water accumulation or corrosive accumulation. So, that should be having a good amount of drainage facility, or we should have provide good amount of radius there. So, here it is better to have like this covering, as well as we will not allow any water accumulations there. So, this is one possible design modification. Now, there could be possibility of avoidance of vibration, avoidance of fatigue failure, in fact corrosion fatigue. So, let us say we have a long pipe component suspended against another pipe component. So, let us say this is my so this is the joint. So, this is another joint, and where we are actually having fluid flow. And this is the pipe thickness. This is the welding, let us say. Now, this is a long comma, and here also fluid is moving, fluid flow. So, this is another pipe. Okay. Now, whenever we have this kind of situations, there could be possibility of vibration. And since this is the fluid is corrosive, so there could be possibility of failure in that particular pipe system, and that is related to corrosion fatigue. To avoid this, one should have a flexible hose, maybe for example, the support, one should have a proper support. So, let us say this is my support and this is another support, which are actually holding the pipe system, which is joining to the main fluid flow, and the vibration effect can be avoided to a great extent. Okay. So, this is we are actually avoiding this particular support, a stiff support. Avoids vibration, and accordingly we can actually prevent corrosion fatigue to a great extent. So, this is another effect of influence of stress. Now, stress can also lead to several other effects like stress corrosion cracking, or hydrogen embrittlement. So, these two effects will talk when we talk about materials. In fact, design also can avoid stress corrosion cracking. So, design in terms of material composition, for example, stainless steel. Somehow, if we can avoid precipitation of chromium carbide along the grain boundaries, then definitely we can avoid stress corrosion cracking also. And similarly, hydrogen embrittlement, if we have a good amount of, let us say in case of inhibitors, we can use inhibitors which can avoid hydrogen reduction reaction on the surface, then hydrogen embrittlement can be avoided. So, those are coming in a different context, but main thing is, in case of stress corrosion cracking or corrosion fatigue, we should have a design where stress, the corrosion effect as well as stress effect both are minimized, and in case of corrosion fatigue, we should see that the vibration in a corrosion medium is minimized. So, these are couple of design aspects what we have shown here. There are many such examples. You can look into several other literatures or internet sources. Now, examples on easy approach for painting. Now, if we have a situation like this, let us say you have a sharp bent like this, okay. This is the sharp bent. When you have this sharp bent, let us say you are doing a spray coating. Let us say we have a spray coating. Flat surface coating would be easy, but when you come to the corner will have the coating thickness, if you consider, so that will be less. So, this is less coating thickness around the corner. Now, here it will be less, and if you consider this part, there could be problem of inaccessibility. For painting, and even if you access it, so there would be lot of deposit of painting, fine. So, it is better to again modify. So, the modification comes in this fashion, again putting a bend. So, that will allow uniform coating thickness all over the surface. So, here the coating will be uniform. Because we are getting access to those cornered portion equally, uniform coating. Now, if we have a design like this, let us say a tank design or this design, again there will be problem, because accessibility will be issue here, and as well as coating thickness would be issue, thickness issue. And this here it will be inaccessibility. Right. So, the better design would be, this is bad, in this case it was bad, this is better. So, here it will be like this. If we have this design, so everywhere we have better access, and also uniform coating thickness. This is better, this is bad. So, this is another design aspect which considers the ease of painting or ease of coating, and also it ensures uniform coating thickness. So, this is another design aspect which considers the ease of painting or ease of coating, and also it ensures uniform coating thickness. So, we have discussed lot of design aspects for the protection purpose of a component from corrosion. So, we have talked galvanic effect, stress effect, area effect, painting effect, accessibility effect, welding to cover up crevice part, round off to take care of stress concentration. Now, we have discussed a lot of design aspects for the protection purpose of a component from corrosion. So, we have talked galvanic effect, stress effect, area effect, painting effect, accessibility effect, welding to cover up crevice part, round off to take care of stress concentration. Now, from next class onwards, we will talk about material aspects for corrosion protection. The design aspects, whatever we have covered, mostly are taken from ASM handbook volume 13A, which is corrosion fundamentals testing and protection. And then we have also taken help from the book on principles of corrosion engineering and corrosion control by Zaki Hamid. So, you can also follow those references. So, let us stop here. From next class onwards, we will take up material aspects for corrosion protection. Thank you.